After the module that we have gone through last week, where we have started with the topic set, in today's class we are going to talk about various types of set. So the first set that we are going to talk about is a finite set. As the name suggests, a set in which we can count the total number of elements present is called a finite set. As an example, we can talk about a set in which all natural numbers less than 50 are given. As we all know that the natural numbers less than 50 are from 1 to 49. So we can actually count the number of elements that are 49. So that's why this set is a finite set. As another example, we have a set in which all factors of 36 are stored. We know that the factors of 36 are countable too. So that's why this set is going to be a finite set. The next set that we are going to talk about is an infinite set. So a set in which we cannot count the number of elements will be called as an infinite set. As an example, we can talk about a set which contains all the natural numbers. Remember, a natural number set will contain the numbers from 1, 2, 3, 4 and so on. It has no end to it. So that's why we cannot count the exact number of elements present in this set, and that makes it an infinite set. Another example where x is the element of the set such that x belongs to n and x is greater than 100. Again, the natural numbers which are greater than 100 are infinite. We cannot count them. So that's why this set is going to be an infinite set. The next thing that we are going to talk about is the cardinal number. The cardinal number is actually the number of distinct elements which are contained in a finite set. Why I am saying finite set? Because in finite set we cannot count the number of elements, but in finite set we can actually have the count of number of elements. So this count of number of elements is actually the cardinal number. So whenever we are going to talk about cardinal number, it will be surely of some finite set. So in this case I have taken a finite set A. So the cardinal number of this set A will be denoted by lowercase n within circular bracket A. So cardinal number of A is going to be denoted by this symbol. As an example, we can talk about a set A which is equal to within curly brackets 1, 2, 3, 4. Then the cardinal number of A will be 4 as there are 4 distinct elements in this set. The next example where A is equal to within curly brackets x such that x is a letter in the word apple. Remember, no letter in this word can be repeated when we are going to write it in the roster form. So set A will be equal to within curly brackets A, P, L, E. Now if you count the number of elements in this set, they are 4 in number, and hence the cardinal number of this set becomes 4. The third example where A is equal to within curly brackets x such that x is the factor of 36, we are going to write all the factors of this set as individual numbers. So if we are going to count the number of factors, they come equal to 9. So in total there are 9 factors of this number 36. Hence the cardinal number of A becomes 9. As we proceed further, we move on to the next category of the set, which is called empty set. So a set which contains no element in it at all is called an empty set. It can also be called as a null set or a void set. It is generally denoted by phi or sometimes as empty curly brackets. Also, if we talk about the cardinal number of an empty set, that means cardinal number of phi, it is always 0. The reason being, there is no element in this set. So the count of number of elements is 0. Hence the cardinal number of an empty set is always 0. As an example, we can have a set containing x as an element, x such that x belongs to n, 3 is less than x is less than 4. Remember, when we talk about natural number, there can be no number in between 3 and 4. Hence, there will be no element in this set, which makes it an empty set. As the second example, I have taken x such that x is an even prime number where x is greater than 5. Now remember, the only prime number which is even is 2. So there is no other even number which can be prime and it is greater than 5. So hence this set will contain no element in it, and this set is going to be treated as an example of an empty set. The next set that we are going to talk about is a singleton set. as the name suggests, the set contains exactly one element in it. So any set which contains one element in it will be called as a singleton set. Therefore, the cardinal number of this set is always 1 because there is only one element in it. As an example, we can talk about a set A which is equal to, within curly bracket, a lowercase a. It is containing only one element, so it is a singleton set. Similarly, another set B which is equal to, within curly bracket, 1 contains only one element in it, so it is also an example of a singleton set. To proceed further, we are going to talk about the sets which are called equivalent. Now, two finite sets A and B are said to be equivalent if the cardinal number of A is equal to the cardinal number of B. That means the number of elements in both the sets should be equal. That is, they have the same number of elements in them. It is represented as A, a double-headed arrow, B. So this symbol, double-headed arrow, is actually representing that A is equivalent to set B. As an example, let us take a set A which is equal to, within curly bracket, A, E, I, O, U, and a set B which is equal to, within curly brackets, 1, 2, 3, 4, 5. Now, if you count the number of elements in both the sets, the cardinal number of A happens to be 5 and the cardinal number of B happens to be 5 again. Like I said, if the number of elements in the sets are equal, then the sets are going to be called equivalent. Hence, A is equivalent to B. The next property of sets, if we are going to talk about, is equal sets. Now, two sets A and B are said to be equal sets, and they will be written as A is equal to B if and only if every element of A is in B and every element of B is in A. As an example, a set A which is equal to 1, 2, 3, 4 and B is equal to 4, 2, 3, 1. Now look at the elements in both the sets. The elements are exactly the same, even though when their order are changed, but still the elements, the distinct elements, are exactly the same. So here the cardinal number is same for sure. So these two sets become equivalent because their cardinal number is same. They both contain 4 elements, but the elements are exactly same. Hence, not only equivalent, they are equal to. If the sets are not equal, then we write A is not equal to B. We have to note that two equal sets are always equivalent, but two equivalent sets need not to be equal. Remember, if we are going for equality of the sets, their cardinal number has to be same before we actually match the elements that they are same or not. But if we are talking about equivalent sets, it doesn't matter whether the elements are same, but the total number of elements should be same. Hence, two equal sets are always equivalent, but two equivalent sets need not to be equal. Next thing is a universal set. Now, whenever we are discussing about any given problem, there has to be a set which contains all the possible elements of the problem. So a universal set is a set containing all the elements of a problem under consideration. It is generally denoted by an uppercase U. The universal set for different problems may be different. So for every individual problem given to you, it contained a different universal set. Again, I am saying it, a universal set contains all possible elements of the given problem under consideration. Let us take an example. There is a set A which is equal to, within curly brackets, students who play chess. Similarly, we have a set B which is equal to, within curly brackets, students who play cricket. Now these are the two sets for the given problem. If I am going to talk about the universal set, here in this problem we can take a set of all the students of a particular class as the universal set. Out of those students, few will be playing chess and few will be playing cricket, but the students will be from that particular class. So all the students of that particular class will be a part of universal set. Remember that in a given problem there can be only one universal set. Now let us proceed further with the topic subset. If A and B are two sets given in such a way that every element of A is in B, then we say A is a subset of B, and the representation is given in the slide. So this is how we represent it. Therefore, if A is a subset of B, then if X belongs to A, X also belongs to B. That means this element has to be present in the second set also, because A is a subset of B. All the elements of set A will be present in set B. Then we have the other term which is called superset. In the same example, if I take where A was a subset of B. Now, if A is a subset of B, the other way of saying it is that B is a superset of A, and it is written in the way given in the slide. Note that every set is a subset of itself. That means if a set A is given, then A is a subset of A. Similarly, if a set B is given, B is a subset of B. Every set is a subset of itself. Then empty set is a subset of every set. No matter which set we pick up, an empty set will always be a subset of it. If A is a subset of B and B is a subset of A, that means both the sets are equal. Similarly, the vice versa is also true. If A is equal to B, then A is a subset of B, and at the same time B is a subset of A. If set A contains n elements in it, that means the cardinal number of A is n, then the total number of subsets possible for this set is given by the formula 2 raised to the power n. This is an important point. In order to get the count of number of subsets possible for a given set, it is given by 2 to the power the cardinal number of the given set. I believe you will be able to remember it. Moving on to the next topic, that is proper subset. Let B be any set and let A be any non-empty subset of B. Then A is called a proper subset of B and will be written in this given form if and only if every element of A is in B and there exists at least one element in B which is not there in A. That means B contains extra elements. Though A is a part of B, but still few extra elements are there in B which are not there in A. Then A will be called as a proper subset of B. So, if A is a subset of B and A is not equal to B, then A is a proper subset of B. Please note that an empty set has no proper subset because empty set can contain no other element in it. A set containing n elements has 2 raised to the power n minus 1 number of proper subsets. For example, if A is equal to within curly brackets 1, 2, 3, 4, then the cardinal number here is 4. There are 4 elements in it. So the number of proper subsets will be given by 2 to the power n minus 1, that is 2 to the power 4 minus 1, which happens to be 16 minus 1. So the total number of proper subsets come equal to 15. So there can be 15 proper subsets of the given set. This is the theory which is required to continue with the next exercise of chapter 1, that is exercise 1b. But before you actually start with this exercise 1b, there are certain guidelines for you all. You need to follow these guidelines. If you are going to see questions 1, 5, 6 and 8, they all are objective. But still you need to go through them properly and then answer the questions directly in the book, but you need to use a pencil. Do not mark anything with the pen in the book. You have to mark everything with a pencil. So all these objective questions, I am repeating them, 1, 5, 6 and 8 are to be answered in the book itself with a pencil. The second point is you must attempt the rest of the questions in the fair register. Remember the register that you have made for the previous exercise, that is exercise 1a. So you need to continue in the same register, and we are going to do the remaining questions of this exercise other than these objective questions in the fair register itself. You need to put the heading as exercise 1b. The other important point is do complete your work neatly, and whatever queries you have can be discussed for the same. Now here in this slide I have given you the screenshot, or you can say the picture of the actual exercise 1b. So those who don't have the book, you can take the help of these images. There are in total 8 questions. If you see, in total 8 questions are there. So like I said, 4 of them are objective. Question number 1, 5, 6 and 8. The rest of them are to be attempted in the fair register, and these objective questions are to be done in the book itself using a pencil, remember. Now some explanation before you start doing exercise 1b. So let us start with the first question. In the first question, if you see in the given exercise 1b, we need to state whether the given set is a finite set or an infinite set. So let us pick up the first part of this question. In this set, we are talking about the multiples of 5. So if I am going to represent it in the roster form, the set will be written as within curly brackets 5, 10, 15, and the elements go on because there is no end to it. There are infinite number of multiples of 5. Hence, the number of elements are uncountable in this set. So this set cannot be treated as finite. It has to be called as an infinite set. So in the first part, the set is infinite set. Let us move on to the seventh part of the same question. In this part, we can substitute infinite natural numbers as the values for variable n. Therefore, the elements in this set are uncountable again. So again, this set A, is an infinite set. Moving on to the next question. In this second question, x represents the elements of universal set, and x lies between 0 and 37. They have also stated that x is also a multiple of 3. So the universal set can be written as within curly brackets 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36. Now why are these elements only coming up in this universal set? Because of the condition given as the set builder notation for the universal set. They said x is a multiple of 3 and it lies between 0 and 37. So these are the possible values which can be there for the given condition. Now A contains elements as multiple of 6. Remember that the elements of A can be picked only from the universal set. Why so? Because universal set contains all the possible elements for the given problem. So A will be equal to within curly brackets 6, 12, 18, 24, 30, 36. We cannot go beyond 36 because that is the end limit of universal set, and here the elements have to be the multiples of 6. So that is the possible answer for this question. Question number 3 is very similar to question number 2, so you should be able to attempt it. Moving on to the fourth question. In the fourth question, let us pick up the first part. Remember, while writing the elements of a set, we do not repeat any letter. So therefore, set R will be equal to APLE. Remember, we have to write it in the roster form before we actually write the answer for the question. So set R is equal to within curly brackets APLE. The cardinal number will be 4 because there are 4 elements in it. Similarly, set S will be equal to PALE. Again, the total number of elements are 4, so the cardinal number of S is 4. Since both the cardinal numbers are equal, cardinal number of R is equal to cardinal number of S, therefore R is equivalent to S. At the same time, if you see the elements of both the sets, they are exactly the same. Though their order is different, but the elements are same. And while writing the elements in the set, the order is not required. So in any order we can write it. So hence, the given sets are equal. So both the sets are equivalent, at the same times they are equal as they contain exactly the same elements. In question number 5, if we talk about, we need to state true or false. It is an objective question, like I said. You have to answer it with pencil in the book itself. Let us pick the second part of it. As each element of the first set is there in the second set, therefore the first set is a subset of the second set, and hence this statement is true. In the seventh part of this same question, converting the given sets in their roster form first. So in the first set, we will get the set as within curly brackets 11, 13, 17 and 19. And in the second set, we will get within curly bracket 13, 15, 17, 19, 21, 23 as elements. Clearly, all the elements of first set are not present in the second set. If you see 11 as the element in the first set, it is not there in the second set. Therefore, this statement is false. It is not a subset. First set is not a subset of the second set. So this statement is false. Question number 6. It is again similar to question number 5. You should be able to attempt it. Moving on to question number 7. In the seventh question, we need to mention the subsets for the given sets. Remember, the number of subsets is given by 2 to the power n, where n is the cardinal number of the given set. That is the number of elements present in the set. So let's do the second part, where b is given as, within curly brackets, 3, 6, 9. So the cardinal number of b will be 3. Hence the number of subsets will be given by 2 raised to the power 3, which becomes 2 into 2 into 2, which is equal to 8. Therefore, the subsets, the total number of subsets will be 8. Let us write them. The first one is an empty set. Like I said, an empty set is always a subset of any set. So empty set is the first subset. Then all the elements are individually written as singleton set. Then taking 2 elements at a time, we have 3, 6, 3, 9, 6, 9, and finally all the 3 elements taken together. So if you count the subsets that we have got, they are exactly 8 in number. Hence, this is the answer for question number 7, second part. Moving on to question number 8, which is again very similar to the objective questions like we have done in question number 5 and so in question number 6. So you should be able to attempt it. Now the rest of the questions can be attempted accordingly. Do follow the guidelines mentioned above while completing your work. This brings us to the end of the first chapter. Once you are done with exercise 1B, 1A you have already completed. So this is the end of the first chapter. All of you are suggested to complete both the exercises and at the same time come up with your doubts or queries if any. We will be continuing with chapter 2 in the next mathematics class. Until then, keep your work completed and do take care of yourself.